Hey, what's up, guys? This is Cheng here again. So this time, 1,896 minimum cost to change the final value of expression. So you're given like a valid Boolean expression, right, as a string expression consisting of 1, 0, bitwise and bitwise OR, right? So here are some examples, and the expression is guaranteed to be valid, which means that it's not possible to have this kind of invalid string, right? But this one is possible, okay? And you need to return the minimum cost to change the final value of the expression, basically to flip the value, because for this bitwise expression, the final result can only be either 0 or 1. So our goal is to flip that value, but we want to do it in a way that we will use the minimum cost. So what's the cost? Basically, a cost is either change a value or you change a operator. So that's the four cost we can possibly use. And the one last thing is that so the bitwise AND does not take precedence over the bitwise OR. So which means that if we have 1 and 0 or 1, something like this, we should evaluate from left to right, which means we'll evaluate this one first, and then we use the result to evaluate this one. Oh, and we also have some like an parenthesis. Yeah, I forgot to mention. So we also have like parenthesis. And yeah, so that's it, right? Basically, so for example, this one, we have this expression, and the final result of this one is what? So 1 and 1 is 1, right? So this one, the final result is 1, but we want to change this one from 1 to 0. And we have to, there's like several ways we can make the change. We can either change this 1 to 0, right? Or we can change this one to 0, right? But either one of them will cost us 1. That's why the answer is 1, right? And then in this example 2 here, the final answer obviously is 0, and our goal is to flip the value from 0 to 1. So in this case, we need to make at least 3 operations to make this one equals to 1. Right. So here, I think it gives you one of the possible solution, which we flip this one. Yeah, flip this operator and this value from AND 0 to bitwise OR 1, and then also flip this one to 1. Flip this one to bitwise OR. Okay. Yeah, so that's it, right? And so obviously this one is gonna be a recursion. Actually this one can also be used either a recursion or a stack. Every time this kind of expression problem, I believe either stack or recursion will work, right? But for this one, I solved this one by using the recursion, because I think the recursion to me is a little bit more intuitive, right? Okay, so let's go back to the requirement, right? We want to flip the result, right? And how can we? So whenever we want to flip a result, we could have different options, right? And basically, let's say if we have like A, B, an operator. So here, let's say we have an AND here, right in the middle. So if we want to flip this result into a different value, so we could have different scenarios. Based on the value of A and B, we could end up doing a different strategy here, right? So for example, assuming this operator is AND, let's say this one, let's give it, let's say if these two are 0, okay? So if this A and B are both 0, and so the value is obviously 0, but we want to change this one to 1, right? So we have target is 1. So how can we change 0 and 0 to 1? We have several like options, right? So the first option is what? We change both 0 to 1, and 1 and 1 will become to 1, right? So which means we do just 1 and 1. So we have 1 and 1. So this is one of the scenarios. Or we can also change this operators from AND to OR, right? So in this case, it's going to be what? It's going to be a OR, but if we change the operator from AND to OR, then we only need to satisfy one of the satisfy either A or B to be 1, because either this one or this one will work, right? So basically, we have these 3 scenarios. If in this case, right? So similarly, if we have this 1 and 1, right? So the value is 1 and the target is 0. So if you want to change this one to 0, and so what do we have? Obviously, this one is easier than this one, because for the end scenario, we only need to change either left or right into 0, right? So basically either 0 and 1, right? Or 1 and 0 will work. In this scenario, there's no point of changing this operator, because if we're changing this operator from AND to OR, then it means that we need to change both left and right side to be 0, right? Then that obviously will cost more, right? So that's it. And then the last scenario is this one. It's either A and 0 or 0 and 1, right? So these two can be grouped together. So this one, the end result is 0 and the target it will be 1. So in this case, if you want to change this one to be 0, right? Sorry, change this one to be 1. We have 2 options actually, right? So yeah, either 2 options, but the answer will be the same. Basically, we can either change this 0 to 1, right? Or we change this 0 to 1, or we can simply change this AND to bitwise OR, right? So any of those changes will make this one become to 1, and the cost obviously is fixed size. Is 1 in this case, because we know that we only need to change actually, you know what? So for this one, the cost will be 1, because the only option we'll be using here is it's going to change this. Sorry, my mistake. So in these scenarios, we shouldn't change either B or A into 1, because this part might take more cost. So in this case, the only option we have, or the optimal solution, is to change this bitwise AND to bitwise OR, because this way we are guaranteed to only spend 1 cost to flip the value, right? Because here, since we have A and B, but A and B could be another like a sub expression, right? So if we choose to flip this sub expression from 0 to 1, it could be more than 1. Actually, it would definitely be either equal or greater than 1. That's why the optimal solution for this scenario is only by flipping the operator here, right? So then we have this kind of like 4 scenarios for A and B. So similarly for A, X or B, we have similar like scenarios, but I'm not going to list that here. But now you guys can see, right? So if we, by given like expression, if we can find these two parts, right? And if we know the values of the two parts, and if we also know the cost of the two parts. So the cost means that, you know, if we, the cost of changing this part, flip the value of this part either from 0 or 1 to 1, or from 1 to 0, and then we can utilize these two parts to basically to calculate the current state, right? So this kind of be a, you can call it a DFS or DP, and but I think for this one, well, it's not actually a DP problem, because we're keeping separating splitting the expression into a smaller one, but there's no overlap, so we don't need to memorize the result. So which means that, you know, let's say we have some expression, right? I mean the if like 0 and like this, you know, or 0 and 0, right? And then we have another one, right? And 1 and 0, something like this, right? So for example, this is the one, right? I mean, keep in mind that, you know, for same level calculations, we always want to calculate from left to right. So which means that, you know, okay, you know, let's say there's another one. There's another like one end at the beginning. Okay, so let's say if this is the original expression, as you guys can see, we have 3 parts here. So one, this one, and this one. Okay, so which means that, you know, when we try to split this problem into sub problems, we want to split it in this way. Basically, we want to split it into this part. So this is a part 1, and this is a part 2. Because we always want to calculate from left to right. That's why, you know, we have split it from, basically split it in from the end. So yeah, that's it. So basically for each of the state, you know, so what's gonna be the state? We're gonna have like start and end index that can represent, okay, so what is the current expression that we're working on, right? And here it will return 2 values. Basically the first one is be the original value, second one is the cost. The cost of changing this value either from 0 to 1 or from 1 to 0. Okay. And then as you guys can see, right? So in order to find each section, right? If it's a value, if it's a 0 or 1, then it's easy, right? We can simply use this one. But if there's like parentheses, right? We have to somehow find the matching parentheses starting from the last parentheses, right? And but since we're using our like DFS, uh, if each time we'll how can we find this matching parentheses? Basically, we have to loop through starting from here, and then we have like a counter of each of this right parentheses, and by the time the counter becomes 0, then that's when we find the matching parentheses, and then we can just pass this one to a DFS, right? But if we keep doing that, you know, that will be basically too much of an operation, because that's going to be a n squared time complexity, because each time we'll be looping through the same string here, right? that'll be too much. So how can we improve that? So one of the trick here is that we can pre-calculate. We can pre-calculate the matching the matching parentheses for each of the right parentheses. Basically, if we do a pre-process at the very beginning, so we know, okay, so for this one, the matching parenthesis is this one, and then for this one, is this one, and for this one is this one, right? We can do a pre-process, and then later on we can simply use O1 time, given like the right parentheses, we can quickly find the matching left parentheses, and then we can pass this sub expression to the next level, DFS. And yeah, so I guess we can start coding in this case, right? And first we need the DFS of S and E, right? So in this case, let's pre-process. Let's pre-process the matching parentheses. So we have a maps of this one, right? And then we have to calculate that we need a stack. So for I dot C in enumerate of expression. This one is too long. Okay, this is much better. Okay, expression, right? So if the current letter is left parenthesis, right? Basically we store that index into the stack. Okay, and whenever we see a right parenthesis, we basically we pop that out, right? Then because we know, okay, we have find a matching parenthesis, matching like a left parenthesis for the current one. That's why we're gonna do this. I is gonna be the stack of pop, right? So here key is the index, value is the matching, right? And yeah, so that's how we pre-process the matching index for each of the right parentheses, and then we just simply need to return the DFS, right? The DFS of 0 to n minus 1, right? And then we do a 1 here because this one here it returns right here the value of expression, right, from start to end, and the cost to flip change the value. So that's how we define DP. Sorry, not DP, the DFS. So the base case, right? So the base case, if the starting is equal to end, which means that there's only one, that's the case of only one letter, either 0 or 1, right? So for this one, we return the int of expression, this one, and 1, right? Because for the single bit values, the cost to flip it is obviously is 1, right? Okay, and then we need to find some parts, right? We need to find this one, basically the A and B, the A, the operator, and the B. We need to find these 3 parts. Okay, like I said, we need to find it. We need to find the last part first, and then this operator, and the remaining is the first part, because we need to, since we are evaluating from left to right. So so operator is going to be this empty, and then I have part 1 equals to part 2 equals to 0. And actually I don't need the part 1, part 2. So I'll do this one, s2 equals 0. So this is the matching index for the last one. So basically, if the last one is the right parenthesis, and then we know, okay, I need to find the matching left parenthesis, right? It's going to be the s2, going to be the maps of the end, right? Else what? So else means that if the current one is either 0 or 1, right? So if that's the case, there's no need to find this matching, which means that the s2 is equal to the end. Basically, this is gonna start and end will be the same for single character, single digits. So, and if the s2 is equal to s, right, we simply do a return of dfs of s plus 1 and the e minus 1. So what does this one do? So basically we could have like some extreme case, where we have so many parentheses, let's say this one, right? So basically for this one, so this is the s, this is the end, right? So when we use the maps to find the s2, the s2 is pointing to here, right? So if they're the same, then we know, okay, we know that there are some like a redundant parentheses, right? We're handling. Then we can simply remove this redundant parentheses, and we can simply recurse to here. Okay, so this one is like necessary because we could also have something like this, oops. Okay, so this is S and this is N. This one is also possible. In this case, there's no redundant parentheses. Where in this case, if we use E here, S2 will be pointing to here. That's why we only remove the redundant parentheses when S2 is equal to S. Otherwise, in this case, this one is greater than the S2. That's why we don't do it. Okay. So now do we have everything? No, we need the operation. So the operator. So the operator will be the expression of the s2 minus 1. Okay, because we find the matching positions, right? So this s2 can either there could be either like a matching parenthesis, right? And then there could be an and here, and there could also be like 0 or 1, right? So either case, the s2 minus 1 will be pointing to this operator, right? So now we have everything, and now we can calculate the two parts. So this is the part 1, right? So this is the part 1, and this is the part 2. Okay, so what is the part 1? So part 1 is the DFS of starting, right, to here, right? So what's the index for this one? It's going to be the s2 minus 2, right? Because the minus 2, because s2 is pointing to here. This is s2. So if we do a s2 minus 2, it will be pointing to here, right? And we have a value 1 and the cost 1, right, for part 1. Similarly, for part 2, we have value 2 and cost 2 equals to DFS of the s2 to the end, right? That's the two parts. Now, based on the values and the cost, we can check all the scenarios. Basically, if the operator is end, right? And if the v1 equals to v2 equals to 0, we return 0, right? Remember, so the first one is always the original value, right? But the cost is this one. So like I said, 0 and 0, right? To change this one to 1, we have 3 scenarios, right? The first one is changing both sides into 1, right? That's why, changing both sides into 1 means that we're gonna use the cost for both sides, okay? And then another scenario is that we flip the operator, right? Which means that we're gonna flip it by 1, right? And then if we flip the operator, we only need to make sure one of the side is equal to 1. That's gonna be either 1 plus C1 or 1 plus C2, right? So that's the case for the V1. For V1 equals to V2 equals to 0. Else if V1 equals to V2 equals to 1, right? So in this case, the original value is 1, but to flip that, we flip either the left or right into 0, right? Else return 0 and 1, right? So this one is the basically either left or right is equal to 0. In this case, all we need to do is just simply flip change this one and to I to this, right? So this is the last scenario. Similarly, right? So else if operator is equal to this bitwise OR, right? Similarly, we have V1 equals to V2 equals to 0. So in this case, there's like this, right? So return 0 dot minimum of C1 and C2. Okay. Else if V1 equals to V2 equals to 1, it's this one. It's this one, but instead this one we have 1 here, right? Else now here we change this bitwise OR to bitwise AND. Oh, and this one is 1, right? Because here 0 x or 1 will be 1. Cool. And I think that's it, right? So now, when DFS is finished, so the value returned will be the original value for the entire expression and the cost to change that value, which is exactly what we are looking for, right? And okay, so let's try to run the code. Did I make any mistake here? Okay. So we have this one, the DFS as the S2 minus 2. Okay. Oh, here. So run the code, submit. Yeah, so it passed. Right. So the time complexity, as you guys can see, we're always splitting this expression into a smaller one, and there's no overlapping because we always split it into 2 parts, right? And then we recursively split it until there's only one character left. So that's why the time complexity for this one, and for each of the DFS here, we do a constant time of checks, right? Basically constant of if else here. So that's why the time complexity is O of n. And there's no need to do something like this, right? So this one will not help because it will not make any difference because the S and E will never be the same. That's why this one, instead of a DP, it's actually a DFS, basically without memorization, because there's no need to memorize it, the state. But we still need to memorize the basically these two values, right? The original values and the cost to change that value. Yeah, I think that's it, right? I mean, I don't know. This one is pretty tricky. I would say that, basically you have to find out the state, and how can you evaluate a given state, right? Based on the different operators and the values, right? We have different scenarios here, right? And then we also need to be careful, like not repeatedly calculating the matching parentheses, and also make sure to always split split the current one from the end, right? And yeah, I think that's it. I'll just stop here. And thank you for watching this video, guys, and stay tuned. See you guys soon. Bye bye.